So, finishing off the kinetics. Last time we introduced these 4 concepts. Remember, kinetics is all about change and time, right? This is the path a reaction takes to get from all the balance equation starting material to all of the products. That's what we call the overall reaction. It's the balanced chemical equation which describes stuff you need and stuff you get. It's accounting, okay? The reaction mechanism is the play-by-play. It's the specific sequence of the steps you need to make this assembly. And why this matters is because a certain composition of starting materials does not necessarily make all the products in one step. Now, if I make that statement, in one step, what does that sound like to you guys? If I say in one step, how if you had to articulate what I'm trying to explain in that? What does that mean? Yeah? Well, what happens fast, there's a bit of kinetics to that too. One step, anybody else? Any sort of other thing? Yeah?
Everything would have to collide perfectly in perfect orientation.
Exactly. Reactions happen because matter bumps into matter. Remember, a chemical reaction, what is defined as a bond? How do we define a bond? It's 2 atoms, and it's some sharing of electrons between the 2 of them, right? The reason they're associated with each other is because there's electrons in their valence shell that have to bond to each other. If we do a chemical reaction, we're rearranging those bonds. And that does not happen magically. There's a sequence, there's rules that are involved of how this happens. If we had 15 things as starting materials and one step, we're saying that 15 things go into one room, and then all the bonds change instantly, and then 15 things come out. That's insane. That things happen in a much more progressive and orderly way, and that's what the reaction mechanism describes. This is where we get intermediates. Intermediates are the steps that you go through, or stuff you make, that then is used up. So the 2 sides of this, an intermediate is stuff that you make along the way to your balanced product. The overall balanced chemical equation says stuff you start with, stuff you get. Intermediates are the things that are formed and then used up. In these intermediate steps, each one where you form one pair of intermediates or one set of intermediates, we call this an elementary reaction. This is one step. So if we start, and again, using our IKEA analogy, all the starting materials, the first step, assembling this particular one, that is something we do once. That's the single event of bond creation or bond breaking, that then we move on to other parts. The reason that this is important is because, again, when we say elementary, we mean it is indivisible. You cannot make it smaller than that. That's the smallest piece of the reaction that we're going to describe. So, by nomenclature, if this is the overall reaction, 2 molecules of N2O5 as a gas are making 4 molecules of NO2 gas and 1 O2 gas. That is the total sum accounting of stuff going in and stuff going out. We are doing it through 3 steps, 3 elementary reactions. So you can look at this as there are 3 discrete pieces of this that form different materials. So we say step 1, step 2, step 3. What is this with respect to the overall equation? Is it a starting material, product, intermediate, or catalyst? So hands up for starting material. Product, intermediate, catalyst. It is a product. Why? It appears as the product. We get 1 molecule of product in this step. Just because it is at the other side, the left-hand side of an elementary step, does not immediately make it an intermediate. It just means you look at this, I am forming this product. Okay? What about NO3? Same question. Starting material, product, intermediate, catalyst. It is a intermediate. Why? You make it and you use it. As we go through and sum these up, they cancel, right? It is a starting material in one step, a product in another. It is an intermediate. It's not there. It happens while the reaction is happening, but it goes away. Okay. Is there a catalyst for this reaction? No, there's no catalyst. But again, what does a catalyst mean? A catalyst is something that you need at the beginning. you get back at the end. So it's the reciprocal or opposite of intermediate. Intermediates just show up and then go away. Catalysts need to be there for the reaction to happen, but they are formed again at the end of the reaction. They still cancel out, but they show up somewhere over here as a starting material. Usually catalysts are expressed in the overall balanced chemical equation above the arrow. What we're trying to say is the reaction needs this, it's just not part of the balanced chemical equation. It's a condition required for this reaction to work. All right, so we have these three intermediates, and we identify them as something that is formed but then used up again. Again, if we go through this, NO cancels, and NO2, boom. Something like that. Oh yeah. Oh no, but it's also a product. There's extras. So, if we go through this part, remember, elementary reactions, they're the single step, indivisible, and this is where we get down to what's called transition states. This is what we discussed before, a collision. In this step, in a single step, what we're really saying is the starting materials pass through one transition state to make a product. It is a single bond reforming event where all that happens. We also can break down these elementary steps into names based on how many molecules are involved. This matters because different molecularities, how many molecules are needed just for that elementary step, changes kind of fundamentally how we think about them. The molecularity is equal to the number of molecules, doesn't matter what it is, but the number of molecules that must be involved as starting materials in some elementary step. So a unimolecular reaction has one molecule of a starting material. One thing turns into other stuff. Bimolecular, two molecules have to react with each other, A and B. Termolecular, three things have to collide together in one transition state. So, in terms of frequency, unimolecular reactions, can you think of something that you know has a single transition state, only involves one material, makes one product? What would be a good example of that?
Hydrogen peroxide?
Yeah, that's not bad. Hydrogen peroxide breaks down to make other stuff. That's good. We talked about it last time. Radioactive decay is the other constant one. Something making products is a unimolecular step. Bimolecular, tons of those, right? Two things reacting together. These are our bread and butter, unimolecular and bimolecular. Termolecular are, again, this is one of those kind of like, oh yeah, I saw a Sasquatch, or I know that there's, like Nessie is real. If you are a scientist and you do this, you will very quickly sound like QAnon. You sound crazy because the rarity, what you're saying is a reaction must have three elements, three molecules that must perfectly collide with each other at exactly the same time for this to happen. Why do you think that's rare? Not just probability. Why does this sound rare? If I have to react three things together, isn't it just easier to do a bi and then a one or a pair of bi reactions? What happens probability-wise is termomolecular reactions would be A plus B plus C to make products. As an elementary step, it is far more likely for that to be two bimolecular events or something else of the smaller order. The termomolecular ones, they do happen, but they're kind of like in the CERN Institute or something, right? They are ridiculously rare events that we can predict. But usually, these make up 99.99% of everything. Yes? Again, based on these same principles, there is, at the moment, at least under Earth's atmosphere, what we can do, reactions that require four things to perfectly fuse at exactly the same time are exceptionally rare. Now, I'm not saying that four things can't come together. It's just usually it splits up as if four things in a balanced chemical equation have to react. It's usually two will react, then another two will react to make intermediates that react with each other. There's pathways that involve in these sort of sequential events. Yeah? Yep, that would be a good one too. If you took a weak acid that dissociates, unimolecular reaction. One thing breaks into two things, right? Either. One molecule breaking into multiple is considered unimolecular. So, we'll go for the clapping. Of these, which would you call, if these are all elementary reactions, which one is bimolecular? So, A, B, C, D, E. You guys crush it, yes. Why is that not bimolecular? Yeah, they're bonded to each other, right? I know, right? So this is where we're going to start using some of these examples to also start talking about things like this. B-C, what we're trying to say is B and C are bound to each other. They are one molecule. If you see this notation, B plus A plus B, those are two different molecules. This is not bimolecular. Why? It's the products. Just like our rate equations, we only talk about molecularity with respect to the fuel needed, not with, it makes two products, that's fine, but it's not a bimolecular reaction. Yeah?
Why not just write BC?
Just to mess with you. No, you're right. This probably could be written as that's just an intermediate, that's totally fine. We note this one again. This is not something I like to do, but you may see this. If we are denoting B-C, we're trying to make it really clear that that is some complex made up of those two pieces. We're trying to show you what's in it. When we actually get to sort of structures, this becomes a lot more relevant, right? Things that are bonded to each other. Okay. So now we can start talking about the reaction coordinates. Now, most important, reaction coordinates are not the same thing as extent of reaction profiles. They still have free energy on your y-axis. But the difference down here, reaction coordinate, now what we're doing is we're mapping the energetic, basically lifetime or energetic experience of one molecule as it moves from reactant to product. Okay, here's the difference. Remember before we did extent of reaction? In here, I have two levels. What is this value right here? Delta G naught, right? It is the difference in energy between starting materials and products. This is our free energy. And if I'm talking extent of reaction, I'm saying, what is the free energy of a system, of a population? This is an average energy that's discussing how much or what's the ratio between starting material and product. An extent of reaction, we start off here saying this is 100% starting material. Over here, this is 100% product. So it's talking about how does the free energy of a lot of molecules change as the ratio between starting material and product changes. This is what we're trying to express when we talk about equilibrium. Remember, I could draw the delta G naught, or sorry, the delta G like this. It's that tie line. We're on here, we're like, oh yeah, that point right here, what is the value for delta G right at that low dip? Delta G at that low dip equals 0. That means what? Are you at equilibrium, before equilibrium, after equilibrium? That is what we're trying to discuss here. So this is talking about the total population of lots of molecules and what the system's free energy is. Everything. Now what we're going to discuss, that's thermodynamics. When we're talking about kinetics, same kind of point. This is still free energy. This is now reaction coordinate. Once again, we've got two levels. This is still delta G naught. That's good. It's the overall energy difference when all the starting material becomes all the product. So no difference there. That value is expressed the same in both cases. The difference is the path. What we're talking about now is the heroic journey of one molecule of starting material as it walks, trudges to its starting material. It's now going along. It's a transition state. Okay, so I'm going to go along here. I'm a starting material, and I need to get to my product. I have to get over here. This is the path I'm going to take. I am at a transition state. Am I higher in energy?
Yeah.
Okay, if I stopped here and waited, is this an intermediate? I can stay here for a while. This is an intermediate. It has lifetime. when the overall reaction is done, it doesn't exist anymore, it's used up, but this is the path I had to take. I've gone up in energy here. And then, okay, I'm gonna go into my products. I'm now done. What's my delta G naught? 0. That was fun, huh? But if I had to graph the energy I did as I walked through that process, I start here, I go through some transition state, that's me climbing up onto the desk, and then, whew, that was tough, I should really do more cardio. Okay, but I'm at an intermediate. Now that I'm at my intermediate, I'm going to take a jump down to my products. How many steps in this path that I've just shown here? 2. I can count the number of steps based on the number of peaks I have to cross, the number of transition states. So this here is a reaction coordinate. It's the energy that one atom or one molecule must take as it moves along its energy profile, as it moves towards its products. So our home audience, somebody's going to have to do describe video for that one. But this is what we discuss. If I have one barrier, one point, this is one step. So this is one way visually here I can denote how many transition states I've passed through, how many steps I have walked through. One step means this is also one elementary reaction. Back here, the other example I showed you, 2 transition states, 2 steps, 2 elementary reactions. Its mechanism involves 2 steps and 1 intermediate. This one, there's only 1 step and no intermediates, right? Starting material, product, and the barrier at the top. That's it. So there's a difference between the 2. This quantity, going from our reactants to the peak of that, we call it, it's back to the energy of delta G. It's not delta G naught, it is delta G double dagger. Anybody heard of that before? It is the free energy, right, still free energy, of what we call activation. It's how much energy do I need to get over this barrier. It's a kinetic barrier to different things. This is your speed bump to how fast reactions can go. If the delta G double dagger is very large, I need a lot of energy to get over this barrier to go onto my products. Most important though, what's the delta G naught for this reaction? Positive or negative? But it still has a positive value for my delta G double dagger. This is why some spontaneous reactions still don't happen very quickly, because we're discussing 2 different things. Delta G naught says how far will this reaction move if we start it moving. That's the spontaneity with respect to products. Delta G double dagger tells you this is how much energy, the price you have to pay to get over that barrier. This is just like university. I want to go to some amazing delta G double product, my amazing cushy job, but there's a price to pay in between. That is your barrier in between as you go between those 2 parts. What you should visualize as you move along this surface, if I have a general overall reaction, so first of all, look at this reaction. If this is an elementary step, what is it? Unimolecular, bimolecular, termolecular? Bimolecular. 2 molecules are reacting together. So how this happens, the movie would look like, first, they're approaching each other. As that happens, there's coulombic repulsion. Electrons are pushing away from electrons. There's a general increase in energy until we reach this point. This point is called the transition state. It is the point in the reaction where bonds are forming and bonds are breaking. It's that squishy part of matter where you're not quite products and you're not quite starting materials yet. But once you pass this point, if I keep moving, I am now more like the product. The bond that we're trying to form is getting better between our A and B. You're breaking the bond over here between C and D. So this one is forming, and this one is breaking. If we keep going, we end up at our products. We're now down here, and we've made a new bond, we've broken a bond, but it shows the journey as you move between them. The height of this barrier dictates how fast this reaction will move. So this transition state is really special. They're always at the top of this reaction profile, and more importantly, it talks about from this point, we could either go in either direction, back to starting material, over to products. It's this apex. The number of transition states you have dictates the number of elementary steps you're dealing with. Every step is defined as passing through one transition state. That barrier, delta G naught activation or delta G double dagger, tells us how fast it will go. Different reactions will have different barriers here. Even if the overall delta G naught, reactions to emit products, are exactly the same, this barrier is what dictates who's fast and who's not. This is what relates back to K. Okay? So of these two, we can say, look, top one will be a slow reaction, the bottom one will be a fast reaction, just based on the height of that barrier. The magnitude there is what relates into those two. So the nice thing about elementary steps, too, back to kinetics, we can use them by inspection to derive rate equations. Now, we said before, if you have an overall reaction, that overall reaction, its rate law, we must determine experimentally. What was the experimental method we use to determine the order in our starting materials? Generally, we call it the method of initial rates. What's nice about elementary reactions, since they pass through only one transition state, we can, by inspection, look at this and say, well, look, I know there's only one transition state. The molecule, the elementary step here is very, very simple. There's no mystery going on. In that case only, if I'm looking at an elementary reaction, this is my elementary reaction, shown down here at the bottom. That is the rate. And a result, this is the rate law. That is true because we're looking at something we know for a fact is only involving one transition state. So this is the one time we can, just based on the equation, say, the rate law must be blank. Yes?
That's kind of like saying the same thing as saying like the mechanism is the same as the overall reaction.
Yes, exactly. So yes, the mechanism overall is what, like a whole bunch of these elementary steps are what determine the overall rate. If we've got many steps, we can't look at the overall and say, that must be the rate law. If I'm looking at just one transition state, I know the mechanism only involves that one step, therefore its rate law must be that simple. So as long as I have an elementary step, if I know it's been defined as that, this becomes my rate law. This is one of the ways that if I don't know how a mechanism is occurring, if I do the method of initial rates, and I solve it that, this is the rate law, that's kind of telling me that maybe my equation is only one step. Kinetically, I can't distinguish any different. So, once again, if all these reactions below, we define them, they are elementary reactions. Which one will have a rate law that says rate equals Ka? All right. So, A, will that have rate equals Ka? How about D? How about C? How about B? How about A? How about C? How about A? Okay, yes, it's C. Each of them, you can look at the starting materials, and from that, derive the rate law immediately based on this. Now again, which of these is a unimolecular reaction? It's the only one also. Which one is a bimolecular reaction? Which one is going to be first order in A? A, B, and C. That's right. Good. So again, if you're dealing with elementary reactions, it gets much simpler. Now look at this one. You have a reaction below. You don't know. Wait, sorry. Reaction below occurs in a single step. What do we mean by when we say that? If the reaction below occurs in a single step, what are we telling you? It's an elementary step, exactly. So, which is true? The reaction is unimolecular and elementary. A. Okay, B, the reaction is bimolecular and elementary. Okay, C, the reaction is unimolecular but not elementary. And last, bimolecular, not elementary. Again, bimolecular because you're reacting two, and if we say happens in a single step, that is what we're telling you about. It is an elementary step. Okay, last one. One more question. You have a reaction. A, B, and C obeys the rate law, rate equals K. First order, second order, zero order. If rate equals K, it's a zero order. Which of the following statements is true? Okay, the half-life will increase with time. Okay. The reaction is bimolecular and elementary. The plot of ln A versus time will be linear. The reaction will be slow when the concentration of C is large. And E, the reaction cannot be an elementary reaction. That's the main thing. Now we'll start off on this one and we'll go through each of these definitions last point. You should be able to recognize what we're trying to communicate through all 5 of these. I'll see you guys on Wednesday. Hey there.